Welcome back. We are going to use the fundamental theorem of calculus to find the derivative of gx equals definite integral 1 to x natural log 1 plus t squared dt. So notice, make sure your lower limit is a constant, upper limit is a variable that agrees with g. Notice the function fx equals natural log 1 plus x squared. Where did this come from? This is the integrand. Instead of t, I have used x. Fx natural equals natural log 1 plus x squared. It is continuous on the closed interval 1 to infinity. So, by the fundamental theorem of calculus part 1, because it is continuous, that's all we need. Where did I get that one? It's the lower limit. Okay. Derivative of g equals f. That's the fundamental theorem of calculus. G is the area function. Lower limit is constant. Upper limit varies. So derivative of g is the function inside with x replacing the t. Derivative of g is natural log 1 plus x squared. Here is the next question. Find the derivative of this. Again notice, lower limit is constant, upper limit is variable. Look at the function inside, replace it by u. Is this continuous on 0 to anywhere else? Yes, it is. Okay, the only problem here is negative 1, which is not in this particular set. U negative is not in this particular set. All you are going is from 0 to infinity. So, all you need is continuity. Therefore, by the fundamental theorem of calculus part 1, derivative of the definite integral. Derivative of h is the inner function evaluated at u. Derivative of h is square root u over u plus 1. Here is another question. H of x equals definite integral 1 to square root x z squared over z to the 4th plus 1. Lower limit is a constant. The object inside is continuous from 1 onwards. I've replaced the z by x. Now notice, upper limit is square root x in my original question. Well, if the upper limit had been just x, then you can use fundamental theorem of calculus. Again, I repeat, upper limit in the question is square root x, but if it had been a simple x, our problem would have been simple. But it is not just an x, it is square root x, that is g of square root x. How do you find derivative of g of square root x? This is the chain rule. Derivative will be g prime of the thing inside us is times derivative of square root x. G prime of square root x is f square root x. Derivative of square root x is 1 over 2 square root x. Therefore, h prime, I'll replace the f of t wherever I see t by square root x and write the derivative of square root x here. So, it's a bit complicated. Let me explain once again. Upper limit is square root x. So when you take derivative of h, what essentially happens is you replace the z by upper limit and then multiply it by the square root of the upper limit, by the derivative of the upper limit. I repeat, derivative of h, you replace the z by the square root and then times it with derivative of the square root by chain rule. F of the square root times the derivative of square root. So that completes your answer. Okay. Here, g of x is definite integral 0 to x. Upper limit is simple x. All I have to do is replace the t by x. That is the derivative of g by the fundamental theorem of calculus part 1. As long as the object inside is continuous, which it is. What happens if the lower limit is not fixed, but the upper limit is fixed? So you can interchange upper and lower limits, introduce a negation. Now you are back to your original game. Negative integral 0 to x square root 1 plus secant t. Okay. Now look at square root of 1 plus secant t. It is continuous from 0 to pi over 2. At pi over 2, it actually has a vertical asymptote. So it's limited only from 0 to pi over 2. So for x between 0 and pi over 2, the fundamental theorem of calculus applies. And derivative is the object inside replaced by x. The object inside replaced by x, don't forget the negation. So the derivative of capital F is negative square root 1 plus secant x. What happens if the lower limit is constant but the upper limit is not just x? When the upper limit is not just x, you replace the t by the upper limit and then take derivative of the upper limit. Okay, that is the chain rule part. Replace the t by the upper limit times derivative of the upper limit. Okay. Replace the t by the upper limit, multiply by the derivative of the upper limit, that is by chain rule. Okay. Now here, what happens when you don't have constant limit in either location? Well, u squared minus 1, u squared plus 1. This is continuous everywhere. So choose any number from the real number line. I chose 0. Split this definite integral 2x to 3x as 0 to upper limit minus 0 to lower limit of the same. So now you have two questions, two definite integrals you want to find the derivative of. Well, upper limit is not just a simple x, so you need to use chain rule as well. Use fundamental theorem of calculus part 1 and the chain rule. Derivative of the first integral, replace u by 3x and then times it with the derivative of 3x. Second one, replace u by 2x and then times by the derivative of 2x. Okay, so that is g prime x. Derivative of 3x is 3, derivative of 2x is 2. Replacing u by 3x fetches you this here. Replacing u by 2x gives you this here. Okay. Now what about the case when both the limits are constants? When both the limits are constant, you use the fundamental theorem of calculus part 2. What does this say? You find the antiderivative of the object inside. Antiderivative of 1 is v. Antiderivative of 8v cubed is 8v to the power 4 over 4. Antiderivative of 16v to the 7, 16v to the 8 over 8. Write it within a box, within brackets. Take the limits as they are. Okay. Evaluate this bracket. Okay. Oh, I have simplified it. 8 over 4 is 2. 16 over 8 is 2. Now evaluate this at 1, that is substitute v equals 1, substitute v equals 0 and take the difference. Evaluate at upper limit minus evaluate at lower limit. The rest is algebra. 1 minus 2 plus 2, they cancel. 0 minus 0, 0, they all get cancelled. All you're left with is 1. Okay. Again, you have evaluation when both upper and lower limit are constants. So you need fundamental theorem of calculus part 2. Definite integral 1 to 8 of x to the negative 2/3 dx. Take the antiderivative of x to the negative 2/3. Add 1 to the exponent. Divide by the new exponent. Negative 2/3 plus 1 is positive 1/3. I'm dividing by 1/3. Division by a fraction is multiplication by reciprocal. So I have found the antiderivative of x to the negative 2/3. Now bring in the limits. Whatever you write, place it in parentheses. Upper limit is upper limit, lower limit is lower limit. 8 upper limit, 1 lower limit. Final answer, 3 cube root of x, upper limit is 8, lower limit is 1. What do you do with these limits? Finally, evaluate them. Replace x by 8, replace x by 1 and take the difference. Evaluation at upper limit minus evaluation at lower limit. Cube root of 8 is 2, cube root of 1 is 1. It should be a 3 there, okay? 6 minus 3 is 3. Again, I'm asked to evaluate definite integral 1 to 3. Both limits are constants. So what do? I find the antiderivative of the object inside. 1 over z to the second power plus 1 over z to the third power. 1 over z to the second power is z to the negative 2 power. 1 over z to the third power is z to the negative third power. Antiderivative of this. Increase the power by 1, divide by the new power. Antiderivative of this. Increase the power by 1, divide by the new power. So z to the negative 1. Mind you, negative 2 plus 1 is negative 1 over negative 1. Negative 3 plus 1 is negative 2 over negative 2. Don't forget to keep track of the limits. So these bracket and numbers on top and bottom are meant to keep track of the limits. 3 is the upper limit, 1 is the lower limit. 3 is the upper limit, 1 is the lower limit. Continue simplifying. Z to the power negative 1 comes down to be z to the positive power. Negative is negative, plus followed by negative is negative. 1 over 2 z squared. Upper limit, lower limit. Evaluate at upper limit. So wherever you see z, I've placed 3. Evaluate at lower limit. Wherever you see z, I've placed 1. Don't forget to take the difference. Evaluation at upper limit minus evaluation at lower limit. Assuming my arithmetic is correct, this is my final answer. I'll continue in the next video.